Let's now come to the capacitor C2, and while computing the constraint for capacitor C2, the independent source of course is set to 0, so it becomes a short circuit. It's a voltage source which is 0, and the capacitor C1 we assume has been chosen properly, so that is also a short circuit. So now let me draw a box around this circuit. What is the resistance that appears across C2? You can see that the connection looks something like this. We have this circuit and its output terminals. C2 is connected here and RL is there, and this is the ground. So between these two terminals, between here and there, which are these, looking in, you will see a resistance. Because it's a linear circuit, you have to see something that will be a resistance, and that resistance is nothing but R out, the output resistance of this circuit. Okay, so all you have to do is to compute the output resistance of this circuit and make sure that C2, its reactance, is much smaller than the total resistance, that is 1 over omega naught C2 is much smaller than the total resistance, which is RL plus R out, or C2 must be much greater than 1 by omega naught RL plus R out. Okay. So what is the value of R out? Again, very easy to compute. We have RS here and RG between the gate and the drain of the MOS transistor, the control source GM VGS, this is VGS, this is the source terminal, and we are trying to find the resistance between the drain node and ground. And what do we do? As usual, we can apply a voltage source V test and find the current I test and take the ratio V test by I test. Okay. So again, there are many ways to do this. I suggest that you try it by yourself, just as an exercise in circuit analysis. Okay. Now you can of course write the usual Kirchhoff's laws and find it. What I'll do is slightly different from that. I'll notice that basically this voltage source appears across this resistive divider. By the way, if you are getting confused, simply write the Kirchhoff's current law at this node and at this node, and you will find the result. Okay. So I'll do it slightly differently. This V test is applied across this resistive divider and no current is flowing from here, the gate terminal, right? So this VGS here is nothing but a resistive divider ratio times V test. VGS is RS divided by RG plus RS times V test. Okay. And the current that is flowing up in this branch is nothing but V test by RG plus RS. And the current flowing here is GM times VGS, which is GM times this whole thing. Okay. So the total current I test, this equals that one plus that one. So we find that I test equals V test divided by RG plus RS plus GM V test RS by RG plus RS. And by solving for this ratio, we find that the output resistance is nothing but RG plus RS divided by GM RS plus 1. Okay. So that is how it is. And also, when you carry out these calculations, it's always good to have some sort of sanity checks, some checks where by evaluating some extreme cases, you can see whether the answer makes sense or not. Okay. And in this case, I can think of one such thing. Let's say GM is 0, that is, there is no transistor at all. We have only the resistors. Then what should happen? This current source disappears, and all you see between these two terminals is the series combination of RG and RS. Now, in this expression, if you set GM to 0, the answer is RG plus RS. So it does satisfy the sanity check. And these things are very important. First of all, for simply checking that the result that you got after a lot of algebra is correct, and also to get some intuition about the circuit. Okay. So once you calculate the output resistance, all you have to do is calculate the constraint on C2 using this, and C2 to be much larger than that one. So that completes our treatment of the common source amplifier using drain feedback, and it works as a common source amplifier provided RG is sufficiently large. We have calculated what that is, and also we have calculated the constraints for the AC coupling capacitors. Okay. We already discussed the constraint on capacitor C2 so that it appears as a short circuit, and that is this condition. Now, like we discussed with the original common source amplifier with a fixed gate source bias, this condition ensures that the gain of the amplifier is the same whether the capacitor is there or not. That is the meaning of capacitor being a short. If C2 satisfies this constraint, then you will get a certain small signal gain, and it will be very close to what you would have got if C2 were really a short circuit or it's an infinitely large capacitor. Okay. Now we also discussed another possible constraint for capacitor C2. Many times we want the voltage VDS here to be the same as V0. Okay. Now, if this condition is satisfied, under some circumstances, it's possible for this signal VDS across the drain source voltage to be substantially more than the output voltage V0. Okay. So, we want VDS to be the same as V0. In that case, as we discussed earlier, the constraint would be C2 must be much greater than 1 over omega naught RL. Okay. So, many times you use this constraint as well, and as before, obviously if you satisfy that, you will automatically satisfy that one. Okay. So, this is the stronger condition. Okay.